Okay, in this video we're going to look at static equilibrium. There's an I in there, just so you know. Okay, so real easy idea that in static equilibrium, static means no motion whatsoever, so that if we added up all the forces, there would be no change in motion, so not going to be accelerating. But also, there's not going to be any rotation, so the sum of all the torques is also going to be equal to 0. And the sum of all the torques always has to have a reference point. The sum of all torques is going to equal 0 about any point in space. So we can really just pick any point in anywhere in the universe, look at a simple equilibrium situation where we have, two things just kind of balancing together. We can pick any point and we can calculate the torques around that point and show that the sum of all the torques would be equal. All right? But we're going to pick a point that is actually on our system that makes it the easiest way to solve the problem. So here's a simple idea. I have a meter stick. And I am going to balance this on a fulcrum. We have the midpoint right here. That is our 50 centimeter mark. And if this is the 0, let's say that that's at 30 centimeters. All right. And we know that if we try to do something like that, balance something on its end, it would fall down, right? So this will just fall down, hit the ground. So what we would have to do is put some type of mass on this side. And it's just where would we have to put this distance-wise away from the fulcrum, all right, some distance x away, so that it is balanced. Next thing we have to make sure we do is realize that for any beam, gravity always acts at its center of mass. So at the 50 centimeter mark, this is where gravity is going to be acting on the meter stick. Gravity would only be acting on the mass that we're going to place over on this side, that we're trying to figure out where does it have to go in order for this to work out. Let me use big M for the meter stick, and I'll keep that little m for the mass that we have to place to balance it out. Usually, we want to sum up the torques around a reference point that we actually can pick first. And for something like this, where it's balancing on a fulcrum, what we want to do is pick the point that it's touching the fulcrum at. At this point, there is still another force, right? So we have gravity pulling down the meter stick at its center. We have gravity pulling down on the mass, but this whole system is not falling downward. The fulcrum itself is exerting a force upwards. So force of the fulcrum. Now, if we make this our point of reference, we can see that the force is going through our point of reference, which means that it is not perpendicular to that point at all. So this has 0 torque contributing to the system, where this gravity, all right, from of the meter stick is at some perpendicular distance away, all right, which looks like it's going to be 20 centimeters. All right, as a perpendicular distance away from that weight of the meter stick. That's causing this thing to rotate this way, all right, from that torque. This one's going to exert a torque to try to twist it the other way, but our goal is to make sure that the torque created by this force is going to be equal to the torque created by this force. And our goal is to figure out where do we have to put that thing so that they balance out. All right, so we're going to start out with summing up our torques. Equals 0. We have two that are two torques. We have this one and that one. Doesn't matter which one we really write first. I think there's a convention here of what's positive and what's negative, but it really doesn't matter, and you'll see that in a second. All right, so we have the weight of the meter stick acting at a distance of 20 centimeters, and I'm going to show you, I'm going to use the centimeters here so you can see what happens. 20 centimeters from the pivot point. All right, you don't use the location of it, you use the distance it is away from our reference point. All right, so this is the force times the distance, which is the torque. And then this is going to make it rotate this way. This one over here will make it rotate the opposite way, so they have to subtract. We will then have the little mass times its gravity for the weight times the distance x that we don't know. And those should add up to be 0, which means that they have to be equal. So it doesn't matter which one was positive or negative, because you just move the one over that's negative and they equal each other, so it doesn't really matter, right? So big mg times 20 centimeters has to equal little mg times x, and we can see that the g's cancel out. We don't need to worry about that. And we just end up with a ratio of the masses times the one distance that we know to figure out where this thing is. Now, I actually don't remember too much about what the masses of these meter sticks are. I, for some reason, feel like the mass of a meter stick, big M, is around 275 grams or 0.275 kilograms. All right, so here, let's make it a little heavier, actually. We'll say that little m is equal to 0.4 kilograms. Now, just like the centimeters isn't going to matter, because we're going to get a distance here in centimeters, all right, so we can handle the units there. Notice that the units of the masses will cancel out as soon as you divide those out. Okay, so we can plug in those values. We have 0.275 kilograms divided by 0.4 kilograms. Kilograms cancels. So again, it's just going to be a ratio. These units actually don't matter. Times 20 centimeters, and that's going to give us x. Let's see what it is. 0.275 divided by 0.4 times 20 gives us 13.75 centimeters. Now, what does that mean? Is that going to be placed at 13.75 centimeters? It is not. It is going to be 13.75 centimeters to the left of our pivot point. So if we actually wanted to know where it was going to be, we would have to take that, what did I say that was, 30 centimeters, minus the 13.75, and know that it's going to be placed at a location of 16.25 centimeters. So we would be able to solve for x, but sometimes it'll say at what location on the meter stick would we have to put it. This would end up being the 16.25 centimeters just by subtracting the 30 by that. All right, so that is a simple static equilibrium problem. So let's look at something that's a little bit more challenging. All right, let's take a look at another scenario. So here we have a beam that is attached to the wall by a pin. So imagine something that's able to slot in there, and you can stick a pin through there so that this beam would be able to rotate. All right, then we're hanging a mass from the one end, and then we have a cord attached to this end that is connected to the wall that's holding up this system here. All right, and there's going to be a few different types of connections that we might see, such as the pin that we're seeing right here, right? So if this thing is held in place, there's not really going to be a specific directional component to these things, but if this beam is being pushed into the wall, right, then the wall or the pin is going to prevent it from going there, so that would have some type of x component. Sometimes we just call that fx. Gravity's trying to pull this thing down, but the end is not falling because the pin is holding it up, so that would just be an fy component for that pin. All right. It could be on the floor, all right, the ground, whatever the surface is, and even it could be at the angle there, but we would still have a force up that is making sure that that part doesn't fly down through the ground, and then so it's not sliding backwards, the pin also has to exert a force in the x direction, so it's going to behave kind of in the same way. All right, and then if we look at maybe something else where we have like a ladder leaning against the wall, if the ground is frictionless, then there's only one force at this point of contact. It is just the normal force acting upwards, perpendicular to the surface. All right. If it's touching the wall over here, that wall is going to exert another normal force, right, perpendicular to that surface. If we have a similar scenario, but there is friction, then This ladder would want to slide this way, so we would have a frictional force that's holding it instead of like a pin here, and we would still have a normal force. And there could be friction between the wall and the ladder up here. So that ladder would want to slide and fall down like this, so there would be a frictional force holding it up, and still the normal force pushing it perpendicular to the surface. So these situations are usually the ones that are the most difficult to try to identify how the forces are acting when they're perpendicular to each other. So let's apply that to this one here. We have the pin. So we have to think a little bit more. This cord is pulling it this way. So there is a tension along the cord, and it is holding it up. There's a vertical component because this wants to fall down. Plus it is pulling it in towards the wall. So therefore the wall or the pin has to push back with some amount of force. If we took the pin out, this whole thing would kind of like fall and collapse. So the pin is holding it up as well. So we have that Y component. All right, this beam right here has some mass, so there's a force of gravity acting on that beam, and it's going to be at the center of mass. So here we have little mg. And then at the edge, doesn't matter if there's that cord there or not, say it's tension, but really the force, because it's in equilibrium, has to equal the weight of whatever the heck's being held there. So we're going to draw big mg. All right, so we have our force diagram drawn here. And now what we have to do is, let's say we want to figure out the tension. Okay, we want to figure out how much tension is on that string right there. We need to pick a reference point that we will write all of the torques in reference to. Usually if there's a pin, we pick the pin. Most times we're not worried about what the up and down forces are that the pin is exerting on the system. All right, so that's a general thing. Pick the pin first if we need to choose our reference point. I do need one more thing here, and it's going to be the length of the beam. I'm just going to call it length L, and we're going to see if that works out. I may have to add a certain value to it later, but we will see. Okay, so sum of all the torques around this pivot point has to equal 0, and you usually start with the sum of all torques first. Our goal is to figure out the tension. Excuse me, tension. So how many forces do we have exerting torque? We have the tension, and that has an upward component that would cause it to rotate upwards. Here we have gravity that would, from this block, is going to try to rotate it this way. Here we have gravity on the center of mass, going to try to rotate that beam this way. So we have two going this way, all right, and one holding it up. So it'll be this torque minus that torque minus that torque. So I'm going to write it out that way. Now with torque, we're only worried about the perpendicular amounts of force to the radial distance, right? So we're only worried about the Y component of the tension of that string. So we're going to see that it's going to be the sine function. So we're going to have the tension times the sine of theta, which is 30. And this tension is acting at a distance L away. So I'm going to multiply it by the L. All right, that's my one positive torque that I'm going to use. Then I'm going to subtract this torque right here, which is going to be big mg, and it is acting at a distance L away, still at the very edge, and that's all I have for that torque right there, this force at that perpendicular distance away. Then we have one more. It's also going to try to rotate it down, so we're going to subtract that one. We have little mg, and that is acting at a distance of L over 2 away from that reference point there. And that's going to all equal 0. Okay? So L over 2. Now I gave us the mass of the beam. I gave us the mass of the block that's hanging, and we don't have the length or the tension, but luckily we have the angle there. All right, so we can start to manipulate this for the things that we know. We're going to move these two over to the right-hand side because we want to get T by itself. And you can already see that everything has an L in it, so the L's will cancel. We can cancel that out before we move it because it's just dividing by L on both sides, 0 divided by L is still 0. So we have T sine of theta is equal to big MG minus plus, they're in the same direction, plus little mg, and make sure we don't forget that guy, over 2. Okay. Still don't need to plug in numbers yet. I know that the sine of 30 is going to be a half, so I'm going to even put that in there. So I have 1/2. The tension is going to equal big M plus little m over 2 times g, and just get that out of there, right? So I have little m over 2, factor the g out. I don't know if that was easier or not. We'll see. All right, 1t by itself, multiply by 2. So I have 2 times m plus m over 2 times g, and I don't like that. I'd rather have 2m plus little m times g equal to the tension. So at this point, we can start plugging in our numbers, right? So we have 2 times big M. 2 times big M is 50 kilograms, all right, plus our 20 kilograms. And we're multiplying all that mess by our G, which is 9.8, to get us our tension. Use the old calculator here. We have 120, right? 2 times 50 is 100, plus 20. So we have 120 kilograms times 9.8 meters per second squared. Gives us units of newtons. Boom. 1,176 newtons. All right, and it gives us the tension. Now we can continue this problem, and they can ask us how much force is being exerted upwards on the pin or from the wall. All right, and how do we continue with that? Once we figure out the one force using the torques, what we can do then is it's a lot easier to solve for the next one if we just use the sum of all the forces equal to 0. So let's do that. Let's solve for the x value. All right, it's a little bit more simple. So we're going to figure out what the sum of all forces in the x is. So we have this F, and hey, that doesn't exert any torque. All right, so we couldn't even use it in a torque equation. So that's why we're using the linear forces. So in the x direction, we have 2 forces, right? We have f of x to the right, and then we have the x component of the tension to the left. So that would be t times the cosine of 30, and that's going to equal 0. There's only 2 forces, left and right. We're looking for f of x. That has to equal t times cosine of 30, and since we just found t down here, we can just multiply that by the cosine of 30, and then we get that the pin or wall is exerting a force equal to 1,018 newtons. All right, and if they keep asking us to solve for something, we can do the y's. All right, and why not? Right? Not why not? Let's write that stuff down. So sum of all forces in the y has to equal 0. How many forces do I have up and down? I have Fy up. I have big mg down. I have little mg down. And they all have to equal 0, right? Because it's not accelerating up and down at all. So they all have to add up to be 0. So we just know that f of y. Oh, I forgot one. I did. I forgot that there's this upward component to the tension. So I'm just going to slide that one over to this side already. So it's that's just whatever like that. So it's going up, so it should be positive. So that's still the t times the sine of the 30, and then it's going to equal 0. There we go. So we know all that stuff. So we're going to move it all away from Fy. So Fy is going to equal big mg plus little mg minus the tension times the sine of 30, and we can just plug in those values, and hopefully life is good. So we have 50 plus 20 times 9.8, so 70 times 9.8 gives us a total value of this of 686 minus the tension times the sine of 30. Tension was 1176, so 1176 divided by 2 gives me 588, and that tells us that Fy is going to be the difference between those, which is going to be 98 newtons. Being contributed, holding that thing up just at that point right there. All right, and that is the only things we can solve for that problem. However, they're not always this simple. You can have a whole bunch of weird angles and stuff like that. Like here's a pin here that's holding this beam right here, and then there's a mass hanging onto it right here, but that's going to fall down there. So let's add cord that has tension on it going this way, and then we have the center of mass of that thing here. We're trying to figure out the tension on this string needed to hold up this mass that's pulling down right here. So you can get really fun and multiple angles here that we would have to kind of figure out how to get all the perpendicular components with respect to some type of reference point, usually starting out with the pin. We will get a lot more practice with this, but hopefully this is a good start.